Energetics of solution formation. So we can think of that solution forming as happening in 3 steps. First of all, you have to separate the solute particles from each other. You have to break those interactions. That's always going to be an endothermic process. That's going to require energy to pull them apart from each other. So the change in energy for that is going to be greater than 0. It's going to be a positive number. Separating the solvent particles from each other is also going to be endothermic. That those solvent molecules are attracted by whatever molecular forces they have. You have to put energy in to separate them. So delta H solvent is also greater than 0. Now, when you mix the solute and the solvent, you're going to have some interactions now forming between the solute and the solvent particles. That's going to be exothermic because energy is being released as the particles interact. Even a substance like hexane that has dispersion forces only and water that has hydrogen bonding, they will have some attraction for each other. But it might be much lower than the interactions that each had with its friends. So delta H mixing, that's always going to be a negative number because that's going to release energy. So we have to invest in separating the particles, and then we get a payback when we mix them together. The enthalpy of solution, the change in energy due to the mixing, the forming of the solution, is the sum of the changes in enthalpy for each step. So how much energy do you have to put in to separate the solvent molecules? How much energy to separate the solute, whatever. Solute and solvent is so tongue-twisting. And then how much energy do you get out when you mix them together? Whether a solution forms or not will depend on that overall delta H. Well, the delta H depends on the sum. This is going not well. So solution formation can be exothermic or endothermic, meaning that when the solution forms, it may take in energy or release energy. So here are sort of a Born-Haber cycle type diagrams. So here we've got the solvent and the solute. Aggregated means they're stuck together, they're with each other. So we've got those aggregated, and then we're going to separate the solute particles. That's going to require us to put in energy. We're going to separate the solvent particles from each other. We have to put in energy. Now we're going to allow these to mix. We're going to get a big negative release of energy as the solution forms. If the overall change is negative, it's an exothermic process. And some substances do this. You put them in water and they get hot. The solution becomes hot. Sodium hydroxide does this. You put solid sodium hydroxide in water, you mix it up, it gets hot all by itself because it's an exothermic process. The enthalpy of solution is negative. There are other substances, though, where you separate the solute particles, you separate the solvent particles, and you allow them to mix together. This delta H of mixing is smaller than the sum of those two, and so overall it's an endothermic process. When you mix up this solution, it becomes cold. Have you seen or ever used those instant ice packs, cold packs they have? Trainers usually have them on the sidelines, and somebody sprains an ankle or something, you can break open the seal and it'll get cold and you don't have to cart ice around with you. They're often in first aid kits and stuff. What's going on in there? It's two substances that when mixed, their enthalpy of mixing is positive. It sucks energy in, and so it becomes cold. Yeah?
You know those balloons that you punch and they expand? Have you ever seen those?
Haven't seen those. Ooh,
I
yeah.
have some downstairs. But you punch them and they expand and they have little Halloween or Christmas decorations on them.
I haven't seen those.
That
That must be a chemical reaction that generates a gas. So apparently
it gets cold.
It gets cold too?
Yeah.
Interesting. Yeah. So there's all kinds of fun stuff you can do with chemistry and making shows of things. I mean, light sticks are another example of, you mix these two things and something cool happens, right? It gives off light, and it seems like magic. There's no batteries involved. One of the tricks is that if you're going to have these as consumer products, they have to be fairly safe. Yeah. So that limits. Well, and airbags in your car. How do those work? Is there a little compressor in there that blows them up real fast? No, it's a chemical reaction that generates gas. So there's a sensor that causes the reaction to begin, and it goes really fast and inflates the airbag by generating gas. Yeah, interesting. So looking at aqueous solutions of ionic compounds. So we've got delta H for the solvent. That's the energy needed to separate the water molecules from each other. And we've got delta H mixing. That's the energy released when the ionic compound mixes with the water. And what we do is we put those two terms together, and we call that the heat of hydration. So that's the change in energy when the ionic compound dissolves in water, when the ions dissolve in water. So it's the enthalpy change when 1 mole of solute ions in the gas state are dissolved in water. Of course, that's not how we do it in practice, right? We haven't done anything with ions in the gas state. But that heat of hydration is always largely negative. It's exothermic. Delta H solute, so that's the energy needed to separate the solute particles. In this instance, it's an ionic compound. The energy needed to separate the ions from each other. That's the same as the lattice energy. Right? Lattice energy is the energy released when the ions in the gas state come together. Energy is released. So delta H for the solute is the same as the lattice energy. It's just opposite in sign. So we said earlier that the heat of solution was delta H for the solute plus delta H for the solvent plus delta H mixing. We're going to combine these two terms and call this delta H hydration. And this is still delta H solute. This will always be endothermic, positive. This will always be exothermic, negative. And so overall, delta H for the solution can be positive or negative. It depends on which one is stronger, which one is larger in magnitude.